In this lesson, we'll be looking at sections 3 and 4 of chapter 14, the pH scale and the pH of strong acid solutions. At the end of section 2, we were looking at the autoionization of water, and if the hydrogen ion or hydronium ion its concentration equals the hydroxide ion concentration, then we have a neutral solution. That concentration is 1 times 10 to the negative 7th molar at 25 degrees Celsius. If you add an acid to water, you're going to have more hydrogen ion or hydronium ion than hydroxide. So you're adding hydronium, and so the reaction will shift to the left to react that hydronium. And in the process, it decreases the hydroxide ion concentration. So you have more hydronium or hydrogen ion than hydroxide. For a basic solution, you will be adding hydroxide. The reaction will, again, shift left to react that hydroxide. In the process, it also decreases the amount of hydronium or hydrogen ion, and you end up with more hydroxide than hydrogen ion in a basic solution. In chemistry, we have the pH scale, so we don't have to deal with really small hydrogen ion concentrations. The pH scale ranges from 0 to 14, and some common substances are listed in the diagram there. To calculate pH, we're going to take the negative log of the hydrogen ion concentration or hydronium ion concentration. There's also something called pOH, and that is the negative log of the hydroxide ion concentration. In the pH scale, the 0 end is the acidic end and the 14 end is the basic end. And when we're talking pOH, a pOH of 14 is now acidic and a pOH of 0 is now basic. So for a given solution, if you take its pH and pOH and add them together, they should add up to 14. If you had a pH and you wanted the hydrogen or hydronium ion concentration, we would do 10 to the negative pH. And if we had a pOH and wanted a hydroxide ion concentration, we would do 10 to the negative pOH. On your calculator, notice how the second function of the log key is 10 to the x. For pH, there is a sig fig rule for logarithms. The number of decimal places that we're going to put in our answer for pH is going to be equal to the number of sig figs in the hydrogen or hydronium ion concentration. So now let's calculate some pHs. We have a hydrogen ion concentration of 1 times 10 to the negative 4th, and we want to find the pH. pH equals the negative log of 1.0 times 10 to the negative 4th molar, and that will give us a pH of 4. And because we have 2 sig figs here, we're going to do 2 decimal places in our answer. Notice how our answer matches this exponent here. Now for this next one, we want a pH, but we have a hydroxide ion concentration. We could calculate the pOH and then subtract from 14. We'll take the negative log of the hydroxide ion concentration for the pOH. We get 1.40, so my number of decimal places here matches my number of sig figs. And then for pH, we are just going to subtract from 14. 12.60 is the pH for our basic solution. And letter A, 4.00 is our pH for our acidic solution. These answers make sense. Next, we have a pH of 5.85. We want the hydrogen ion concentration for the solution. we're going to do 10 to the negative pH, 10 to the negative 5.85. But please don't leave the number this way. Let's get it into scientific notation. We get 1.4 times 10 to the negative 6th. There are 2 decimal places in the pH, so we're going to match that with 2 sig figs in our answer. This is a concentration, so we do need a unit. And typically, pHs and POHs do not have units, but concentrations do. So we're going to do molar for our unit on our answer. Now we're going to do some POHs. However, these are the exact same concentrations as a couple of slides ago. So we solved for the pH in A, it was 4.00, and so the POH, subtracting from 14, would make it 10. And for B, we actually already calculated the POH, and that was 1.40. So now we have that solution with a pH of 5.85. Again, we want the hydroxide ion concentration. So let's do POH, and then we can get the hydroxide ion concentration. So 14 minus 5.85 is 8.15, and then for the hydroxide ion concentration, we'll do 10 to the negative 8.15. But again, please don't leave it like that. Let's get an answer in scientific notation. And that answer is 7.1 times 10 to the negative 9th molar. There are, again, 2 decimal places in my pH, so I'm doing 2 sig figs in my concentration. And notice how small this hydroxide ion concentration is. We have a pH of 5.85, that's an acid. And so we'd have a lot more hydrogen ion than hydroxide ion. And we are definitely seeing that with our answers. All right, so now that we've practiced our pH and POH calculations, we're going to practice calculating the pH of strong acid solutions. Remember, strong acids completely dissociate or break apart in solution. So if we have a strong acid like hydrochloric acid, its concentration is going to be the concentration of the hydrogen ion as well. So again, complete dissociation will give you equal concentrations of the hydrogen ion and the chloride ion, but we don't really care about the chloride ion for pH, right? We want the hydrogen ion concentration. There would be a little bit of hydrogen ion or hydronium ion from the water, 1 times 10 to the negative 7th molar, but this concentration here is much higher, so this is what we'll focus on. So we'll do pH is equal to the negative log of 2 times 10 to the negative 3rd molar. And at pH is 2.70. So again, 2 decimal places to match the 2 sig figs that we had in the concentration. Now we want to find the pH of a strong acid solution, HCl. 1.5 times 10 to the negative 11th molar is the concentration of the solution. So again, hydrochloric acid completely dissociates into hydrogen ions and chloride ions. However, water also autoionizes and makes some hydrogen ion at 1 times 10 to the negative 7th molar. This is a higher concentration than what we have here for the hydrochloric acid solution. So pH equals the negative log of 1 times 10 to the negative 7th molar. This is the higher concentration of hydrogen ion, and so we get a pH of 7. If we use the 1.5 times 10 to the negative 11th, we get a pH of 10.82. This doesn't make sense as a pH for an acid. So if we have a strong acid solution, the concentration that is given is the concentration of the hydrogen ion as long as it is larger than 1 times 10 to the negative 7th molar, the concentration of the hydrogen ion just from the water itself. And finally, we're going to calculate the pH of a 1.5 times 10 to the negative 2nd molar solution of nitric acid. This is another strong acid, and this concentration here is greater than 1 times 10 to the negative 7th molar. So the hydrogen ion concentration is going to be equal to 1.5 times 10 to the negative 2nd. And our pH is 1.82 when we take the negative log of 1.5 times 10 to the negative 2nd. 2 sig figs here means 2 decimal places in the pH, and 1.82 makes sense as a pH for a strong acid, nitric acid solution.